February 25th, 1944. The Anzio beachhead, Western Italy. Technical Sergeant Robert Daniels crouched inside the cramped radar trailer as the ground shook from another German artillery barrage. Through the 6-inch thick walls of sandbags hastily piled around the SCR-584 trailer, he could hear the distinctive sound he had been dreading. The high-pitched whine of Daimler-Benz engines at combat power. Luftwaffe bombers inbound. Daniels's hands moved across the console, flipping switches according to the procedures drilled into him at Camp Davis 6 weeks earlier. The 6-foot parabolic dish on the trailer's roof began its mechanical rotation, the antenna spinning at 4 revolutions per minute while nudging up and down in the helical scan pattern. On the plan position indicator display, green phosphorescent returns began to materialize. Enemy aircraft, 12 of them, maybe more. His training said to do what gunners had always done: track the targets manually, call out bearings, adjust range by hand, feed the data to the M9 gun director, let the 90mm guns do their work. But there was another way, a feature built into this radar system that seemed too good to be true. Too dangerous to trust when failure meant German bombs tearing through the crowded beachhead. The automatic tracking system, Daniels had been told about it, he had seen it demonstrated. But every instinct developed from months of combat screamed that you never trusted a machine to do what human judgment should control, not when American lives depended on getting it right. What Technical Sergeant Daniels could not know as those German bombers closed on Anzio was that his decision in the next 30 seconds would either validate or doom the most sophisticated anti-aircraft radar system ever deployed in combat. More importantly, he could not know that hundreds of miles away, an MIT engineer named Henry Abajian was discovering that the weapon that could save Anzio, the weapon that could change anti-aircraft warfare forever, was being systematically misused by the very soldiers trained to operate it. The story that matters is not about Daniels's choice that February night. The story that deserves telling is how American industry and scientific genius created a radar system so advanced that trained soldiers refused to believe it could work. How automatic tracking technology turned flak guns from weapons of desperation into instruments of precision. And how one engineer's stubborn insistence on proper field testing revealed that the greatest obstacle to deploying revolutionary technology was not German jamming or mechanical failure, but human distrust of automation. March 19, 1940. Room 2276, Massachusetts Institute of Technology, Cambridge. Lee Dubridge stood before a blackboard covered with circuit diagrams and frequency calculations, addressing the newly assembled staff of what would officially become the radiation laboratory 8 months later. The meeting had been called with urgent priority. Britain was losing the air war. 5 months earlier, on September 19th, a British delegation led by Sir Henry Tizard had arrived in Washington carrying secrets that would transform American military technology. Among the devices they brought in carefully wrapped boxes was a cavity magnetron, a device so revolutionary that American scientists initially struggled to believe the performance specifications. 1,000 watts of microwave power at 10 centimeter wavelength. Nothing in American laboratories approached this capability. Alfred Loomis, the millionaire physicist running America's microwave committee, had immediately recognized the implications. Microwave radar with this power could detect aircraft at unprecedented ranges with precision impossible using longer wavelengths. But detection alone won wars. The challenge was translating that detection into accurate fire that could bring down fast-moving bombers before they released their ordnance. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Dubridge's briefing focused on 3 priority projects for the laboratory that would officially open in November 1940. Project 1 addressed airborne interception radar for night fighters. Project 3 would develop long-range navigation systems. But Project 2 captured the attention of everyone in that room. Project 2 would create a 10-centimeter gun-laying radar for anti-aircraft batteries, a system that could automatically track enemy aircraft and feed precise targeting data to anti-aircraft guns. The man selected to lead Project 2 was Ivan Getting, a 30-year-old physicist who had earned his doctorate at Oxford as a Rhodes Scholar. Getting understood that creating effective anti-aircraft radar meant solving problems that extended far beyond radio engineering. The radar needed to be mobile, surviving transport over rough terrain. It needed to withstand battlefield conditions, including mud, heat, cold, and the concussive effects of nearby artillery. Most critically, it needed to be simple enough for soldiers with basic technical training to operate under combat stress. The existing American anti-aircraft radar, the SCR-268, had proven fundamentally inadequate. Operating at longer wavelengths around 1.5 meters, the SCR-268 could detect aircraft but lacked the angular precision necessary for effective fire control. Accuracy was measured in degrees rather than the fractions of degrees required to guide shells to fast-moving targets. Gun crews using the SCR-268 were essentially firing into volumes of sky where aircraft might be, hoping for lucky hits. Against modern bombers capable of 300 miles per hour, this approach cost tremendous amounts of ammunition for minimal results. Getting's team started with basic requirements. The new radar needed to detect bomber-sized aircraft at 40 miles range. It needed to track automatically once a target was acquired. It needed accuracy of 25 yards in range and 0.06 degrees in bearing. These specifications represented quantum improvements over existing systems. The solution Getting's team developed relied on a tracking technique called conical scanning. The radar beam would be slightly offset from the antenna's central axis and rotated around that axis. If the target was perfectly centered, the return signal strength would remain constant. If the target drifted off-center, the signal strength would vary as the beam rotated, with the timing of that variation indicating which direction the antenna needed to move. Servo motors would automatically adjust the antenna position to keep the target centered. This was not entirely new technology. The German Würzburg radar had employed conical scanning since 1941, but Getting's team pushed the concept far beyond what German engineers had achieved. The American system would track automatically, driven by feedback loops that continuously corrected antenna position without human intervention. Once locked onto a target, the radar would follow it relentlessly, feeding range, azimuth, and elevation data to external fire control computers. By April 1941, Getting's team had a prototype working. They demonstrated it using a turret from a Boeing B-29 bomber, removing the guns and installing a camera. A friend flew his light plane around the area while the camera periodically photographed the aircraft. On May 31st, the system tracked the plane automatically and precisely. The concept was proven. Now came the harder challenge: transforming a laboratory prototype into a field-deployable weapon system. The prototype, designated XT-1 for Experimental Truck 1, incorporated everything the radiation laboratory had learned about microwave radar in a single mobile package. The entire system fit into one trailer, with the 6-foot parabolic antenna mounted on the roof. The antenna could fold flat for transport, then deploy for operation. Inside the trailer, operators worked at consoles displaying radar returns on multiple screens. For detection mode, the system used its helical scanning pattern, spinning the antenna while varying elevation to search the sky. Radar returns appeared on a plan position indicator display, showing all detected aircraft on a map-like screen with the radar at its center. Once an operator designated a target, the system could switch to a spiral scan pattern, refining the target's exact position. Then, crucially, it could lock into automatic tracking mode. The radar operated at frequencies between 2700 and 2800 MHz in the 10 to 11 cm wavelength band. It transmitted 300 kilowatt pulses lasting 0.8 microseconds, with a pulse repetition frequency of 1707 pulses per second. The technical specifications were impressive, but what mattered for combat effectiveness was performance. The SCR-584 could detect bomber-sized targets at ranges exceeding 40 miles. It could track automatically at ranges up to 18 miles. Within tracking range, it achieved accuracy of 25 yards in range and 1 mil, 0.06 degrees, in bearing angle. This precision was revolutionary, No battlefield radar system deployed by any nation approached this performance. But precision alone did not win battles. The data needed to be useful. Bell Telephone Laboratories had been developing the solution in parallel with the Radiation Laboratories' radar work. The M9 gun director was an analog computer designed to solve the targeting problem for anti-aircraft guns. Given an aircraft's current position, velocity, and altitude, the M9 would calculate where that aircraft would be by the time a shell reached its altitude, accounting for shell velocity, air density, wind speed, and even powder temperature variations. The M9 received electrical inputs directly from the SCR-584. Azimuth, elevation, and range data flowed continuously from the radar to the computer. The M9 processed this information and generated firing solutions for up to 4 90mm Monet anti-aircraft guns simultaneously. The guns would automatically traverse and elevate to the correct angles. Crews needed only to load and fire. The complete system, SCR-584 radar paired with M9 director controlling 4 90mm guns, represented the most advanced anti-aircraft defense ever deployed. In theory. On paper, in controlled tests at Fort Monroe in February 1942, everything worked perfectly. The Army placed an order for 1,200 systems the day after the complete demonstration in April 1942. Production contracts went to 3 manufacturers. General Electric, Westinghouse, and Chrysler Corporation would each produce SCR-584 units. The Radiation Laboratory maintained technical control, allowing rapid decision-making even with 3 major contractors involved. Nearly 2,000 sets were ordered as production ramped up to 200 units per month, but producing the hardware was only half the challenge. Someone needed to train soldiers to use these systems. Training schools were established at Camp Davis in North Carolina. Thousands of maintenance crews learned to operate and repair the radar sets. The instruction emphasized proper procedures. Follow the checklist. Track targets carefully. Feed data to the M9 director. Trust the system. Except soldiers do not easily trust systems they do not understand, especially when their lives depend on those systems working under combat conditions. October 1943. The first production, SCR-584, units began arriving at anti-aircraft batteries in North Africa. The equipment was impressive. The technical specifications were extraordinary. The training had been thorough, but bureaucratic delays and shipping priorities meant the radar did not reach frontline units until early 1944. By then, the Allied invasion of Italy was well underway, and the strategic situation was desperate. The landing at Anzio on January 22, 1944, caught German forces by surprise. Allied troops swarmed ashore on a 15-mile stretch of beach south of Rome, establishing a beachhead that should have opened the route to the Italian capital. But Major General John Lucas, commanding the 6th Corps, chose to consolidate the beachhead rather than push inland immediately. This caution gave German Field Marshal Albert Kesselring time to rush reinforcements. By January 24th, Kesselring had gathered sufficient forces to contain the beachhead. Elements of 8 German divisions, totaling 40,000 troops, surrounded the Allied position. More divisions were en route. The Luftwaffe, which had been relatively quiet during the initial landing, began concentrated air attacks against the confined beachhead. The problem facing Allied forces was acute. The beachhead was only 5 miles deep. Every square yard was within range of German artillery. Ships offshore were vulnerable to air attack. Supply dumps, command posts, and field hospitals were all crammed into a small area with nowhere to disperse. German bombers could strike virtually any target with certainty of hitting something valuable. The Allied anti-aircraft defences included numerous 90mm gun batteries, equipped with the older SCR-268 radar. These systems could detect incoming aircraft, but lacked the precision for effective fire control, especially at night. German pilots quickly learned to make their attacks after dark. When visual acquisition was impossible, radar-directed fire was inaccurate. Loss rates were sustainable. Damage to the beachhead was severe. What made the situation more critical was that Germans had learned to jam the SCR-268. Captured radar sets from earlier campaigns had revealed the system's operating frequencies and vulnerabilities. German electronic warfare units could flood those frequencies with noise, rendering the radar displays useless. Allied gunners would fire blindly into the general area where they believed enemy aircraft might be, wasting enormous quantities of ammunition for minimal effect. On February 24, 1944, 2 complete SCR-584 units were rushed to Anzio and installed overnight. The radar trailers were dug in up to their rooftops, protected by sandbag revetments. The gun crews received hasty briefings on the new equipment. The next night would tell whether the sophisticated radar system could perform under actual combat conditions. February 25, 1944, 12 German bombers approached the Anzio beachhead in darkness. The SCR-584 radar detected them at extreme range. Operators designated targets and initiated tracking. The automatic tracking system locked on. Range, azimuth, and elevation data flowed to the M9 directors. The 90mm guns trained automatically. The crews loaded and fired. 7 of the 12 German bombers were destroyed. The result was startling. In a single night, the new radar system had achieved a kill ratio that seemed impossible with previous equipment. Air attacks on Anzio stopped for a week. When a single German reconnaissance plane finally tested the defences, it was immediately destroyed. 10 more SCR-584 units were emplaced that week. The Luftwaffe threat to Anzio effectively ended. The immediate tactical success at Anzio validated everything the radiation laboratory had claimed about the SCR-584. The radar worked. The automatic tracking and functioned under combat conditions. The M9 director calculated accurate firing solutions. German jamming, which had crippled the SCR-268, had no effect on the microwave frequencies used by the new system. The weapon system performed exactly as designed, but Henry Abajian was discovering that Anzio was an exception, not the rule. Abajian had joined the radiation laboratory in September 1941 with a degree in electrical engineering from Rhode Island State and a master's from Yale. Unlike the physicists and theoreticians who populated most of the lab, Abajian came from practical engineering backgrounds. He had worked in steel mills where small motors were 10,000 horsepower. He understood industrial systems, maintenance requirements, and the gap between laboratory performance and field reliability. At the radiation laboratory, Abajian was assigned to the SCR-584 development program. His initial task was designing the power generation system for the radar. The original concept had been to drive the generator from the radar truck's engine. This proved impractical. Abajian designed a separate truck carrying a gasoline-powered motor generator set that also provided maintenance facilities. This work introduced him to Lee Davenport, the project manager for SCR-584 production, and gave him deep familiarity with every aspect of the system. By early 1944, Abajian had transitioned from development to field support. In February 1944, he travelled to England to provide systems support and training for SCR-584 units being deployed for Operation Overlord, the planned invasion of France. 2 months before D-Day, Abajian was waterproofing 39 SCR-584 trailers that would go ashore at Normandy Beach to direct anti-aircraft fire. He carried papers identifying him as a captain in the Signal Corps in case of capture. He was one of the few civilians who knew the exact date of the invasion. After D-Day in June, Abajian found himself 5 miles behind the front lines, testing SCR-584 capability in fluid combat conditions. The radar performed well in European operations, but reports from the Pacific Theatre were concerning. Units were experiencing problems. Effectiveness was below expectations. Something was wrong. In late 1944, Abajian was dispatched to the Pacific to investigate. The first shipments of SCR-584 systems had been sent to North Africa in 1943 for training. By October 1944, 150 sets were deployed to United States Army anti-aircraft batteries throughout the Pacific as General Douglas MacArthur's forces advanced along the north coast of New Guinea toward the Philippines. What Abajian discovered when he arrived was both simple and profound. The veteran gun crews were ignoring the automatic tracking system entirely. New Guinea, October 1944. Abajian stood beside an SCR-584 emplacement, watching an anti-aircraft battery prepare for Japanese air raids that came with predictable regularity each evening. The radar trailer was positioned correctly, the 90mm guns were properly sighted, the M9 director was connected and functioning, but the battery layout revealed the problem immediately. The guns were positioned as if the crews still depended on optical gun laying. Manual observation posts surrounded the battery. Searchlight crews stood ready. Fire control procedures assumed human operators would track targets visually, estimate range and altitude, and manually feed corrections to the guns. The SCR-584 sat in the center of this arrangement like an afterthought, a technological curiosity that might provide useful information but could not be trusted for primary fire control. Abajian requested permission to speak with the battery commander. The officer was polite but skeptical. Yes, they had the new radar. Yes, they had been briefed on its capabilities, but combat experience taught caution. The Japanese attacked at night, coming in fast and low. Optical tracking, while difficult, was proven. Searchlights could illuminate targets. Experienced crews could estimate range. The system worked. Why change procedures that kept aircraft away from friendly forces? Abajian asked whether they were using the automatic tracking feature. The battery commander hesitated. They had tried it during initial testing, but tracking aircraft by radar seemed unnatural. You could not see what the radar was locked onto. You were trusting a machine to follow a target through three-dimensional space while calculating range, elevation, and bearing continuously. If the radar lost lock, if the automatic tracking failed, if anything went wrong, the delay in reverting to manual procedures could mean bombs falling on friendly positions. Better to use the radar as another information source, the commander explained. The operators could designate targets on the PPI display and call out approximate bearings. The searchlight crews would illuminate those areas. The gun crews would track visually and fire. This combined approach used the radar's detection capability while maintaining human control over the critical tracking and firing decisions. Abajian understood the psychology. These were experienced crews who had fought through campaigns where equipment failed, where Murphy's Law ruled, where survival meant maintaining control over every element of the combat equation. Trusting a radar to track targets automatically meant surrendering that control. It meant accepting that a machine could perform better than human operators. But Abajian also understood the mathematics. The SCR-584 in automatic tracking mode was not marginally better than manual tracking. It was overwhelmingly superior. The difference was not incremental. It was transformational. He asked for permission to demonstrate. The battery commander agreed, though his tone suggested he expected the demonstration to confirm his skepticism. That evening, as Japanese aircraft approached, Abajian worked the radar console himself. He detected the incoming aircraft using helical scan mode. Multiple contacts appeared on the PPI display at ranges exceeding 30 miles. He designated one target and switched to spiral scan, refining the position. Then he engaged automatic tracking. The antenna locked onto the target and began following it smoothly. On the J-scope displays, the range indicator tracked continuously as the aircraft closed. The azimuth and elevation servos adjusted constantly, keeping the target centered in the radar beam. The M9 director received uninterrupted position data and calculated firing solutions in real time. Abajian gave the order to fire. The 90mm guns traversed automatically to the angles specified by the M9 director. The crews loaded and fired. 3 rounds. The third round was a kill. The Japanese aircraft exploded in mid-air, illuminated by its own burning fuel. The battery commander stared at the debris falling toward the ocean. 3 rounds, 1 kill. Using his manual tracking procedures, the battery typically expended 50 to 100 rounds per aircraft destroyed, assuming they achieved a kill at all. The automatic tracking system had just demonstrated efficiency that seemed impossible. Abajian demonstrated again with a second target, 4 rounds, 1 kill. The pattern was clear and undeniable. The problem, Abajian realized, was not technical. The SCR-584 worked exactly as designed. The automatic tracking was reliable and accurate. The M9 director calculated correct firing solutions. The proximity-fused shells detonated at optimal ranges. Every component of the system performed to specification. The problem was human. Soldiers trained in manual procedures were reluctant to abandon those procedures, even when automatic systems demonstrated superior performance. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Over the following weeks, Abajian traveled throughout the Pacific Theater with a General Electric technician, visiting anti-aircraft batteries in New Guinea, Fiji, New Georgia, and the Green Islands. Everywhere, they found the same pattern. Gun crews were setting up batteries as if they still had to depend on optical gun laying. The automatic tracking feature was being ignored or used only as a backup to manual procedures. Abajian's mission became training the crews to trust the technology. The demonstrations were straightforward. Show them the automatic tracking in action. Let them see the precision. Let them count the rounds expended per kill. Let them compare their manual procedures against what the radar could achieve. The evidence was overwhelming. Once crews actually used the automatic tracking in combat, their effectiveness increased by factors of 5 to 10. October 20th, 1944. Leyte Gulf, Philippines. Allied landings had secured a beachhead, but Japanese air attacks were intense and continuous. 6 SCR-584 units were operational, and Abajian was present when the first heavy bombing raid approached. The American anti-aircraft batteries had been instructed to use automatic tracking procedures, no manual backup, no optical redundancy, pure faith in the radar systems. The Japanese attack included dozens of aircraft approaching in waves. The SCR-584 operators detected them at extreme range, designated targets, and engaged automatic tracking. What followed was the most effective anti-aircraft defense the Pacific Theater had witnessed. Aircraft were being shot down at ranges where crews could not even see them visually. The searchlights remained dark. The guns fired only at targets designated by radar. The kill ratios were extraordinary. Over the first 2 weeks following the Allied landings, approximately 300 Japanese aircraft were destroyed by SCR-584 directed fire. General MacArthur sent a message to the anti-aircraft regiment commander commending the superior shooting, but Abajian discovered that even this success was incomplete. The batteries were using the SCR-584 for tracking and the M9 director for fire control, but they were not yet using the system's full potential. There was one more component that would complete the anti-aircraft triad and make the weapon system truly devastating: the proximity fuse, a technology so secret that its existence was guarded at a level comparable to the atomic bomb project, a weapon so effective that its deployment would fundamentally alter anti-aircraft warfare. July 1940. Section T, Division A, National Defense Research Committee. Physicist Merle Tuve stood before a prototype artillery shell, examining the device that his team at Carnegie Institution's Department of Terrestrial Magnetism had been developing for over a year. The challenge seemed impossible. Create a fuse that would detonate an artillery shell automatically when it approached within lethal distance of an aircraft, without requiring the fuse to make contact with the target. Traditional anti-aircraft fire relied on timed fuse. Gunners estimated the range and altitude to an enemy aircraft. Fuse setters calculated how long a shell would take to reach that altitude. The fuse was set accordingly. If the estimates were accurate and the aircraft did not change course or altitude, the shell would explode at approximately the right location. If any element of the calculation was wrong, the shell exploded harmlessly away from the target or failed to explode at all. Contact fuses, which detonated on physical impact, were even less effective against aircraft. Hitting a fast-moving aircraft with an artillery shell was extraordinarily difficult. Near misses, which occurred frequently, accomplished nothing. The aircraft flew on undamaged, while guns expended massive quantities of ammunition, hoping for a lucky hit. Tuve's team was attempting to create a fuse that would sense when it was near an aircraft and detonate automatically at optimal range. The concept relied on radio technology. A small transmitter and receiver would be built into the nose of the shell. The transmitter would emit radio pulses. When reflected pulses indicated the shell was close to a target, the fuse would detonate. The engineering challenges were staggering. The fuse needed to fit inside a 5-inch artillery shell, leaving room for 7 pounds of high explosive. The fuse would experience acceleration forces of 20,000 Gs when fired, and rotational stresses from being spun to 25,000 revolutions per minute as the shell travelled through the gun barrels rifling. The electronic components needed to survive this violence, then function reliably in flight. The fuse needed to be safe to handle, safe to transport, and safe to store. It needed to arm only after leaving the gun barrel, preventing accidental detonation that would kill the gun crew, and it needed to be manufacturable in quantities of millions. By early 1942, Tuve's team, now relocated to Johns Hopkins University as the Applied Physics Laboratory, had solved the fundamental problems. The breakthrough came from accepting rather than fighting the extreme conditions. Vacuum tubes, the fragile glass components that formed the heart of all electronics in that era, were miniaturized and shock-hardened. The battery power source used the firing shock itself to activate, with a glass ampule shattering on firing to release electrolyte into the battery cells. The proximity fuse, designated VT for variable time, contained 5 miniature vacuum tubes, a battery, a transmitter, a receiver, and the detonator mechanism. When the shell was fired, the shock activated the battery. The centrifugal force from the shell's rotation acted on a spring-loaded switch, arming the detonator only after the shell had travelled safely away from the gun. In flight, the transmitter emitted radio pulses. When the shell approached within lethal range of an aircraft, reflected pulses would be detected. The change in frequency due to Doppler shift indicated closing velocity. When the signal strength and frequency shift reached threshold values, the detonator fired. The first combat use occurred on January 5, 1943. The cruiser USS Helena, operating off Guadalcanal, engaged Japanese dive bombers using 5-inch shells equipped with VT fuses. One aircraft was destroyed by shells that passed close enough to detonate without direct impact. The accuracy and lethality were immediately apparent, but the military leadership faced a dilemma. The proximity fuse was extraordinarily effective. It was also extraordinarily secret. If a dud shell fell into enemy hands, German or Japanese engineers could examine the technology and potentially develop countermeasures or copy the design. The decision was made to restrict use of proximity fuses to naval operations over water, where dud shells would sink and be unrecoverable. This restriction lasted until June 1944, when circumstances forced a change in policy. German Wohn flying bombs had begun terrorizing London. The pilotless missiles were too small and too fast for conventional anti-aircraft fire to engage effectively. The threat was severe enough that the risk of proximity fuzzes falling into German hands became acceptable. 20 SCR-584 radar units were deployed to England's Channel coast, specifically to counter the Wohn attacks. 80 90mm guns, directed by the SCR-584 radars and using proximity-fused shells, created a defensive belt through which V-1s had to pass to reach London. The results were dramatic. In the first week of operations, 17% of all flying bombs entering the coastal gun belt were destroyed. By August 23rd, the kill rate had risen to 60%. In the last week of August, 74% of V-1s were destroyed by anti-aircraft fire. On one extraordinary day, 82% of incoming missiles were shot down. The effectiveness rate increased from 1 Wohn destroyed for every 2,500 shells fired to 1 for every 100 shells. The combination of SCR-584 radar tracking, M9 director fire control, and proximity-fused ammunition created an anti-aircraft system of devastating effectiveness. Admiral Arleigh Burke, commanding destroyer forces in the Solomon Islands, wrote after the war that mechanical time fuses had brought down aircraft at night only by accident. The proximity fuse changed everything. In 1943, naval guns fired 36,370 anti-aircraft rounds. Although only 25% used proximity fuses, those rounds accounted for 51% of kills. The statistics from Pacific theater operations were equally compelling. Proximity fuses proved 3 to 4 times more effective than conventional time fuses. Night kill ratios increased by 370%. The lethal fragment area of a proximity-fused shell was 3,000 square feet, compared to 60 square feet for a timed fuse. Near misses became kills. Salvos that would have been wasted became aircraft destroyed. By late 1944, American anti-aircraft batteries throughout the Pacific were being equipped with the complete triad: SCR-584 radar for automatic tracking, M9 director for fire control, proximity-fused ammunition for maximum lethality. When crews finally abandoned their manual procedures and trusted the automatic systems, the effectiveness was overwhelming. December 1944, Mindoro Island, Philippines. Henry Abajian visited 4 SCR-584 installations controlling 16 90mm guns. The Japanese air attacks had been continuous and intense, but the crews were still not using the system correctly. Abajian found batteries that employed the radar for tracking and the M9 for fire control, but were not connecting the systems in the fully automatic mode that would allow the radar to track while the guns fired continuously. The battery commander was reluctant. If the radar lost track during firing, if vibration from the guns affected the antenna servos, if any component failed, they would lose precious seconds reacquiring the target. Better to fire in controlled salvos, verify that tracking remained locked between salvos, maintain human oversight of the process. Abajian requested permission to demonstrate the full automatic capability. A General Electric technician helped him connect a set of searchlights directly to the SCR-584's servo system. When the radar locked onto a target, the searchlights would point at exactly the same location, providing visual confirmation of where the radar was tracking. The demonstration began with a Japanese aircraft approaching at high altitude. The SCR-584 detected and locked onto the target. The searchlights, slaved to the radar pointing angles, illuminated the aircraft precisely. The visual confirmation was undeniable. The radar was tracking the target exactly. Abajian ordered the guns to commence firing in fully automatic mode. The radar remained locked. The searchlights remained pointed at the aircraft. The proximity-fused shells began exploding in a precise pattern around the target. The aircraft disintegrated under the barrage. The battery commander was convinced. When crews could see that the radar tracking was accurate, when they could verify visually that the automatic system was performing correctly, their psychological resistance to trusting the technology evaporated. Once convinced, their effectiveness increased dramatically. Throughout late 1944 and early 1945, Abajian continued training crews throughout the Pacific, demonstrating proper use of the automatic tracking system, showing them how to trust the technology that had been designed specifically to work better than human operators could manage manually. By March 1945, when Abajian returned to the United States, the SCR-584 had become the standard anti-aircraft defense throughout American forces. Production had reached nearly 2,000 units. The system had proven itself in every theater of operation, but the transformation in effectiveness had come not from improving the technology, but from convincing soldiers to use it correctly. The invasion of Japan, had it proceeded as planned, would have relied heavily on SCR-584 directed anti-aircraft defenses. The Japanese had demonstrated willingness to commit aircraft in kamikaze attacks that accepted certain death in exchange for damaging American ships. Against such tactics, conventional anti-aircraft fire was marginally effective. but the automatic tracking and proximity-fused ammunition combination could engage multiple targets in rapid succession, destroying aircraft before they reached ramming range. The atomic bombings of Hiroshima and Nagasaki in August 1945 ended the war before that invasion became necessary. The SCR-584's role in the final campaigns remained important but not decisive. Its real impact had come earlier, in the battles where air superiority was contested, where anti-aircraft effectiveness determined whether ground forces could operate safely and whether ships could remain on station. The numbers tell the story. At Anzio, where SCR-584 units were deployed in desperation, 7 of 12 German bombers were destroyed in the first engagement. Air attacks essentially ceased. In England, defending against Vone, flying bombs, kill rates reached 82% on peak days. In the Philippines, approximately 300 Japanese aircraft were destroyed in the first 2 weeks of operations. These were not marginal improvements. These were revolutionary changes in anti-aircraft effectiveness. The broader significance of the SCR-584 extended beyond the immediate tactical victories. The radar represented a fundamental shift in how military technology would be developed and deployed. It demonstrated that automatic systems could outperform human operators in specific tasks. It proved that trusting technology, even when that trust felt counterintuitive, could save lives and win battles. Ivan Getting, who led the radiation laboratory team that developed the SCR-584, later reflected on the psychological barriers they had encountered. The technical challenges of creating the radar were substantial, he acknowledged, but the human challenge of convincing soldiers to use it properly proved equally difficult. Soldiers were trained to trust their own judgment, their own experience, their own ability to assess situations and make decisions. Surrendering that judgment to an automatic tracking system felt like abandoning responsibility. Yet the mathematics were undeniable. The SCR-584's conical scanning system could track aircraft with precision no human operator could match. The servo motors could adjust antenna, pointing angles continuously and smoothly. The radar beam remained centered on the target regardless of evasive maneuvers. The M9 director could calculate ballistic solutions faster than any manual computer. The proximity fuse could detonate at optimal range without requiring prediction of target altitude. Every element of the system worked better automatically than manually, but accepting this required a leap of faith that combat veterans found difficult to make. The story of Henry Abajian's Pacific Theater deployment illustrates this attention perfectly. He was not inventing new technology. He was not improving the radar's performance. He was not fixing technical problems. He was simply demonstrating to gun crews that the equipment they had been issued actually worked as designed, that the automatic tracking was reliable, that trusting the radar would produce better results than relying on manual procedures developed for earlier, less capable systems. The demonstration with searchlights slaved to the radar pointing angles was particularly brilliant. It gave crews visual confirmation that the radar was tracking accurately. They could see with their own eyes that the radar beam remained pointed at the aircraft. Once they could verify the radar's accuracy visually, they became willing to trust it when visual confirmation was impossible, such as when engaging targets beyond searchlight range or tracking through clouds. This pattern would repeat throughout military history. New technology offers capabilities that surpass human performance in specific domains. Soldiers initially resist the technology, preferring familiar manual procedures. Eventually, through demonstration and experience, they learn to trust the automation. Effectiveness increases dramatically once trust is established. The SCR-584 was not the only example of this pattern in World War II. Pilots initially resisted instrument flying, preferring to maintain visual reference to the ground. Navigators resisted radar navigation systems like H2X, preferring celestial navigation and dead reckoning. Bomber crews resisted the Norden bombsight's automatic features, preferring manual bomb release. In each case, the automatic systems proved superior once operators learned to trust them, but the SCR-584 represented perhaps the purest example of this progression. The technology worked flawlessly from first deployment. The performance specifications were accurate. The reliability was excellent. Yet effectiveness remained limited until operators abandoned manual procedures and embraced full automation. The post-war assessment of the SCR-584's impact acknowledged this human factor explicitly. Technical reports noted that the radar's greatest weakness was not any engineering limitation, but rather operator reluctance to use automatic tracking. Training programs were revised to emphasize trust in automation from the beginning, rather than presenting automatic tracking as an advanced feature to be attempted after mastering manual procedures. The lessons extended beyond anti-aircraft warfare. The development of the SCR-584 demonstrated what could be achieved when American industrial capacity, scientific expertise, and military necessity aligned. The radiation laboratory at MIT had been established in November 1940 with 4,000 square feet of space and $500,000 in funding. By 1943, the lab employed 4,000 people and was designing half of all radar systems used in the war. The SCR-584 project specifically showed how rapidly complex systems could be developed under wartime pressure. The first prototype demonstration occurred in May 1941. The complete system, including M9 director integration, was demonstrated in April 1942. Contracts for 1,200 systems were signed the next day. Production units reached combat theaters in early 1944. From initial concept to battlefield deployment took less than 3 years. This pace was possible because the radiation laboratory maintained technical control over the entire development process. When problems arose, decisions were made by scientists and engineers who understood the technology completely. There were no layers of bureaucracy, no committees requiring consensus, no procurement regulations slowing decisions. Alfred Loomis, Lee Dubridge, and Ivan Getting could authorize changes immediately if those changes improved the system. The relationship with industry was equally streamlined. General Electric, Westinghouse, and Chrysler Corporation transitioned from experimental prototypes to production units in 11 months. Chrysler deserves particular recognition. The company spent those 11 months converting designs suitable for laboratory construction into systems that could be manufactured at scale. They simplified assembly procedures, substituted more readily available materials where possible, and developed quality control processes that ensured each unit met specifications. Lee Dubridge, the radiation laboratory director, wrote to Chrysler's president in October 1945 that no company had cooperated with the lab in a more patriotic and self-effacing way. The efficiency and speed of both Chrysler's engineering and manufacturing people had been extraordinary. Dubridge stated his certainty that the SCR-584 anti-aircraft radars would not have been completed in time without Chrysler's contribution. The production numbers were staggering. Nearly 2,000 SCR-584 units were manufactured during the war. Each unit required thousands of hours of skilled labor to assemble and calibrate. Each contained hundreds of precision components. Each needed to meet exacting specifications for frequency stability, tracking accuracy, and reliability. That American industry could produce these systems at the required rate while simultaneously manufacturing aircraft, ships, tanks, artillery, and millions of other items demonstrated industrial capacity that no other nation could match. The Germans never solved the equivalent production challenge. German engineers understood conical scanning. The Würzburg radar employed the technique. But German radars remained complex, difficult to manufacture, and scarce throughout the war. German anti-aircraft defenses relied primarily on optical tracking and manual fire control. When Allied jamming blinded, their radars, as happened when Window was deployed in July 1943, German effectiveness collapsed. The Japanese situation was even more limited. Japanese radar technology lagged significantly behind both German and Allied capabilities. Japanese anti-aircraft fire relied almost entirely on visual tracking and timed fuses. Against high-altitude American bombers, Japanese flak was largely ineffective. The disparity in technology contributed directly to the success of American strategic bombing campaigns. The proximity fuse story paralleled the SCR-584's development in many ways. Both technologies were developed rapidly under wartime urgency. Both required solving extraordinary engineering challenges. Both involved large-scale industrial production of complex systems, and both remained secret throughout the war, guarded at the highest classification levels. The secrecy surrounding the proximity fuse was particularly stringent. The Navy prohibited its use over land for fear that dud shells might be recovered and examined. This restriction lasted until the Von threat became severe enough to justify the risk. Even then, proximity fuzzes were used only in specific, controlled circumstances where recovery by the enemy was unlikely. Germany developed multiple proximity fuse designs during the war. More than 30, perhaps as many as 50, different concepts were explored. These included acoustic fuses, triggered by engine sound, electrostatic fuses, and radio fuses, similar to the American VT design. But none reached production. The engineering challenges proved insurmountable for German industry, operating under increasing strain from Allied bombing and resource shortages. The fact that Germany could not develop a working proximity fuse, while America produced 22 million units, illustrates the fundamental disparity in industrial and scientific capacity that shaped the war's outcome. Ideas were not the limiting factor. German scientists understood the principles. But translating those principles into manufacturable, reliable devices required resources, industrial expertise, and production capacity that Germany lacked. By war's end, the combined effect of American radar and proximity fuse technology had fundamentally altered anti-aircraft warfare. Pre-war anti-aircraft doctrine assumed that massed fire from many guns would create a barrage through which some aircraft would inevitably fly, accepting damage. Effectiveness was measured in terms of rounds expended per aircraft damaged or destroyed, with typical figures in the thousands. The SCR-584 plus M9 Director plus proximity fuse combination reduced this to hundreds of rounds per kill, then to dozens. At peak effectiveness, as demonstrated against Von flying bombs, the system achieved kills with single-digit numbers of rounds. This represented not an incremental improvement but a transformation in capability. The implications for post-war military technology were profound. The success of automatic tracking systems validated the concept of fire control computers linked directly to sensors. This architecture would become standard for all military applications where precision engagement was required. Naval fire control systems, air defense missiles, and eventually smart weapons of all types would employ automatic tracking and computer-calculated targeting. The SCR-584 itself remained in service long after the war ended. The Korean War saw SCR-584 units deployed for air defense. The radar was adapted for use in the AN, MPQ-12, and AN, MPM-38 systems, which controlled early battlefield missiles. A modified version was used to track the Corona spy satellites in the 1950s and 60s. The basic design was so sound that some SCR-584 units remained operational into the 1990s. In 1995, the first Doppler-on-wheels mobile weather radar system adapted the MP61 pedestal from an SCR-584 for use in tracking tornadoes. The robust mechanical design and precision servo motors that had tracked enemy aircraft in 1944 proved equally capable of tracking severe weather phenomena 50 years later. This longevity testified to the quality of engineering that had gone into the original design. The human story behind the technology deserves equal recognition. Ivan Getting, who led the SCR-584 development, went on to become a key figure in developing GPS satellite navigation. His experience with precision tracking systems and automatic fire control informed his understanding of how space-based positioning could revolutionize navigation. Getting received credit, along with Roger Easton and Bradford Parkinson, for developing the global positioning system that now guides everything from military weapons to civilian smartphones. Lee Davenport, who managed SCR-584 production, completed his doctorate after the war and led construction of Harvard's second-largest cyclotron. He taught physics and continued contributing to radar technology development throughout his career. The practical engineering skills he developed, ensuring that SCR-584 units could be manufactured at scale, served him throughout his subsequent work. Henry Abajian, whose Pacific Theater training missions finally unlocked the SCR-584's full potential, went on to a distinguished career in aerospace and medical research. After the war, he worked at the Airborne Instruments Laboratory, contributing to aviation electronics development. He later held numerous patents in pharmaceutical applications, but his most significant contribution remained those months in 1944 when he convinced combat soldiers to trust automatic tracking systems. The lessons from the SCR-584 story remain relevant today. New technology, no matter how sophisticated or well-designed, cannot achieve its potential unless operators trust it enough to use it properly. Training must address not just technical operation, but psychological acceptance. Demonstrations build trust more effectively than specifications. Visual confirmation helps operators accept automatic systems. These principles apply far beyond military applications. Commercial aviation's transition to fly-by-wire controls, autonomous vehicle development, medical diagnosis systems, and countless other modern technologies face the same challenge that confronted SCR-584 operators in 1944. The technology may work flawlessly, but effectiveness depends on human willingness to trust automation over manual control. The SCR-584 succeeded ultimately because Henry Abajian understood this human factor and addressed it systematically. He did not simply order soldiers to use automatic tracking. He demonstrated why they should trust it. He provided visual confirmation when possible. He showed them the results in terms they understood: rounds expended per kill, targets destroyed before reaching attack position, improved survival rates for friendly forces. Once trust was established, the technology's inherent superiority became apparent. Gun crews who initially insisted on manual procedures and optical backup became advocates for full automation. They saw the effectiveness increase. They experienced the reduction in workload as the radar tracked automatically and the M9 calculated firing solutions without human intervention. They recognized that trusting the technology made their jobs easier and more effective. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The final assessment of the SCR-584 must balance technical achievement against operational impact. Technically, the radar was extraordinary. It represented the most advanced battlefield radar system deployed by any nation during World War II. The automatic tracking was reliable and precise. The integration with the M9 director created a complete fire control solution. The system's performance exceeded specifications in every measurable category. Operationally, the impact was enormous, but required human adaptation to achieve full potential. At Anzio, where desperate circumstances forced immediate adoption of automatic tracking procedures, the SCR-584 eliminated the Luftwaffe threat to the beachhead. Against Von flying bombs, where the targets were small, fast, and predictable, the system achieved unprecedented kill ratios. In the Pacific Theater, once crews learned to trust automatic tracking, effectiveness increased by factors of 5 to 10. The story illustrates that technological superiority alone does not guarantee battlefield success. The technology must be used correctly. Operators must trust it. Training must address psychological barriers as well as technical procedures. And sometimes, it requires a dedicated engineer traveling from base to base, demonstrating patiently that the equipment actually works as designed. The title's suggestion of a forbidden trick misrepresents the reality, but captures an essential truth. To combat soldiers trained in manual procedures, automatic tracking felt forbidden. It violated their instincts. It required surrendering control in situations where control seemed essential for survival. The trick was not that Henry Abajian discovered some unauthorized modification. The trick was that he convinced soldiers to use the capabilities their equipment already possessed. The SCR-584's development cost millions of dollars. Its production involved thousands of workers. Its deployment saved thousands of lives. But unlocking its full potential required one engineer with patience, practical demonstration skills, and understanding that the gap between technology and effectiveness often lies in human psychology rather than engineering limitations. In 21st century terms, we might say Abajian was troubleshooting the user interface rather than the hardware. The radar worked perfectly. The operators needed to learn how to trust it. Once that trust was established, the system performed exactly as the scientists and engineers at MIT's radiation laboratory had promised it would. The broader lesson extends beyond World War II, beyond military technology, beyond even the specific challenge of human-machine interaction. Complex systems designed by experts often contain capabilities that users initially resist employing. The resistance is not ignorance or stubbornness. It is rational caution based on experience with simpler systems where human judgment proved essential. Overcoming that resistance requires more than technical documentation. It requires demonstration, visual confirmation when possible, clear evidence of improved results, and patient training that addresses psychological barriers. Henry Abajian understood this instinctively. He did not lecture soldiers about conical scanning theory or servo motor specifications. He showed them aircraft being destroyed with minimal ammunition expenditure. He slaved searchlights to the radar so crews could see that automatic tracking worked accurately. He built trust through evidence rather than assertion. This approach succeeded where technical arguments would have failed. Combat soldiers do not care about theory. They care about results. Show them that a system works, prove that it improves their effectiveness, demonstrate that it increases their survival probability, and they will adopt it enthusiastically. Tell them the system should work based on engineering principles, and they will remain skeptical until combat experience validates or contradicts the claims. The SCR-584 ultimately proved itself through exactly this kind of evidence-based validation. The systems deployed at Anzio destroyed German bombers at rates that seemed impossible with previous radar. The batteries defending against Von flying bombs achieved kill ratios that validated every claim the radiation laboratory had made. The Pacific Theater operations, once crews learned proper procedures, demonstrated effectiveness that transformed anti-aircraft warfare. By war's end, the SCR-584 had become the standard against which all other anti-aircraft radar systems were measured. It represented the state-of-the-art in automatic tracking, precision engagement, and integrated fire control. Its success influenced military technology development for decades, establishing principles and architectures that remain relevant in modern weapon systems. But the most important legacy may be the lesson about technology adoption. The SCR-584 proved that even perfect technology requires human trust to achieve its potential. That trust cannot be commanded or assumed. It must be earned through demonstration, through evidence, through patient training that addresses operator concerns rather than dismissing them. Henry Abajian earned that trust, one battery at a time, one demonstration at a time, one skeptical gun crew at a time. His contribution to the war effort was not developing new technology. It was unlocking the potential of existing technology by solving the human factors that limited its effectiveness. In the end, that may have been more valuable than any engineering breakthrough. The radiation laboratory created an extraordinary radar system. Chrysler manufactured it at scale, but Henry Abajian made it work in combat by understanding that the real challenge was not technical performance but human acceptance. The SCR-584 shot down thousands of enemy aircraft. It defended beachheads, protected cities, and saved countless Allied lives. But it achieved this impact only after soldiers learned to trust automatic tracking systems over their own manual procedures. That trust was hard-won, carefully, built, and absolutely essential. The weapon that saved Anzio and defended London against Von attacks was not just a radar. It was a radar plus fire control computer plus proximity phases plus, critically, properly trained operators who trusted the automation enough to let it work as designed. Remove any of those elements and effectiveness collapsed. Include all of them, and the result was the most effective anti-aircraft system of World War II. Henry Abajian's Pacific Theater deployment ensured that final element was in place. His patient demonstrations, his visual confirmation techniques, his understanding of combat soldier psychology made the difference between a sophisticated radar operating at partial effectiveness and a revolutionary weapon system performing at full capability. That is the story worth remembering. Not a forbidden trick, but a fundamental lesson about technology and trust that remains relevant 8 decades later.